Hello everyone. I am Nadine Kabbara. I am ESR2 in the InnoCyPES project. I am an industrial PhD working with EDF R&D in France and Utrecht University in the Netherlands. And today I will be giving you a quick presentation on some of my works that were done in collaboration with TU Delft University. And it will be about simulation testbed and cyber attacks on virtualized IEDs and digital substations. As an outline, so I will give a brief introduction about the subject, the context and motivation, because most of you probably know I'm not into cybersecurity. So why am I presenting something about cybersecurity today? I will give a refresher on virtualization concept, virtualization of IEDs, and I will give an introduction of what did we do to study the cybersecurity of virtualized IEDs and digital substations, which is it is an interdisciplinary continuation of my research. We previously did some work on techno-economic study with Jose in virtualized substations, and this is also a follow-up another interdiscipline, which is cybersecurity. So to start up, academic background for those who don't know, okay, I am Nadine. It's a third year PhD now. I previously have a master's 2 degree in control engineering and electrical engineering diploma with some other side hobbies than just doing research. Now, to dig more deeply into the context and motivation of virtualization and digital substations, which is a concept you might have or might not have heard of before. So as we know, power systems, in order to be operated, they need to have protection, automation, and control systems. They are integral elements needed to maintain a secure operation of the power grid. And these, what we call PAC or PAC, they are distributed from the control center levels down to the substation levels. And these applications, for example, could be a protection over current or some automation for a transformer. These algorithmic logic, they are embedded in some communicating devices, which are basically like small mini industrial computers. And these devices, as per what we know in the power systems, we call them intelligent electronic devices or IEDs. And to give an example, these IEDs, they can have some challenges actually. The first is including the number of IEDs that we can have in a substation. For example, in a typical medium voltage to high voltage substations, we can have up to 200 physical devices that we have to maintain, operate, including some visits to the substation, physical visits to do some maintenance on these electronic devices. So yeah, we mentioned this is quite an important constraint for utilities that can have thousands of substations that they have to operate. And over the long term, they also are quite closed architecture and quite difficult to evolve or to have more flexibility or control over what's actually deployed in these equipment. And what we have discovered, given that my PhD is with a utility, EDF, and interactions with other DSOs, that such type of architecture is quite unsustainable, given the very difficult uncertainties that are facing future power grids, including the rise of electrification and integration of renewables. We see that there's more demand to have a system that is more flexible, not only in the sense of adding flexibility of load control, but even flexibility of maintaining the infrastructure or the ICT. So this kind of motivates the change and to what we see in this figure, which is basically to the left, you see the architecture of today with what we call IEC 61850 substations. We see the separation or segregation between different communication buses. And here you see the numerous IEDs. So these are the devices containing the logic. And in the future, what we aim to obtain as an architecture supported by the centralization and virtualization is to have a sort of centralization of these functionalities at the level of a server, which can also be redundant for more availability reasons and can also be hybrid, including physical, like traditional IEDs, and virtualized IEDs within virtual machines or container technologies. And this supports the motivation that we just talked about, which is supporting a more agile or flexible or recurrent function evolution of your applications. The hardware life cycle is decoupled from the software, because with virtualization you can support a sort of decoupling and the capacity to handle more complex functions, because as you see to the right, you sort of support centralization of your data. And when you talk centralization of data, we think about more advanced techniques such as artificial intelligence or as like machine learning that can process more central data. Here we give to the right more in-depth description of what we call virtual IED. So basically, as per our definition that we take throughout the study, a virtual IED is an emulated environment that can run in virtual machines or containers. We will explain right after for people that don't have background in these technologies. That they run both a communication stack. A communication stack is what allows this machine to communicate with another machine on the same network. And it contains a functional stack, which is basically the logic that can be the protection algorithm, the automation algorithm, etc. And as we said, we reiterate here the advantages that we would like to support, which is regarding the reduction of deployment efforts, which is reducing the number of hardware. Because as you saw in the previous architecture, there is a quite significant reduction in the number of hardware that we have to maintain at a more centralized level. So we have some remote management or integrated processes that we can ease the configuration process as well. Which maintains a better overall lifecycle management to our substation systems. And another interesting thing for those who know that before deploying a system, we always need to test a lot. Gabriel knows a lot about this as well. So when you provide a test environment that is quite equivalent to the final production environment, which means that we will run the virtual machine containing the virtualized protection relay logic, for example, and do the testing, we expect that when it's finally deployed in the substation to have exact same behaviors, because we have been testing it in the same environments, getting the same data as well, which is also quite advantageous for laboratories that can't afford buying IEDs. Physical IEDs are quite expensive. So imagine if you want to test something that's also scaled up. This can have some numerous advantages that we saw concretely in different research institutions as well. So here I sum up or I give the refresher for those of you that are less into the IT side. What is basically virtualization, or what do I mean when I say it's equivalent to a virtualized IED or in a virtual machine or container? Basically, maybe all of you have already used or at some point you have a Windows PC. At some point you have to install an app that only works on Linux. So the IT tells you to just run it in a virtual machine that runs Ubuntu. So what this provides by virtualization, it provides to you a virtual instance of a software system that's equivalent to a physical machine, but it's all based on software. So it's basically a computer, but it's all logical computer that abstracts the physical resources that are needed. And the advantages of as I said, the first example is that you have an optimization of the resource usage because you have a physical machine that has been segregated to be using all its resources. More enhanced flexibility because we can be running way too many different systems, applications, operating systems on the same server within different virtual machines, and some reduction of the deployment costs or centralized supervision. So you see again that I am repeating different advantages that I started with as some of our objectives that we would like to reach within future substation systems. So that's why, again, it was quite interesting to dig deep into how we can actually apply it for power systems. And here, there's a lot of ecosystem of IT partners that provide solutions for virtualization, such as KVM, Microsoft Hyper-V, Docker for containers. And it's a huge ecosystem, which means at the same time would be a bit cumbersome because with many different heterogeneity comes also the problem of heterogeneity of the tools that you have to use, maintain. We would then think about some interoperability problem as well between all the different tools. So this is another quite important point that we have to also consider when we want to apply these systems to power systems. Then here for also, I give a very quick separation and difference between virtual machines and containers. For those of you who don't know, very, very quickly, a virtual machine is what is also contains its own guest operating system. So by default, it's a bit more isolated. At the same time, it's a bit more heavy because by containing more libraries and bins for the operating the guest operating system, it will be a bit more luxurious in terms of resources as well. Meanwhile, the containers are lately been the buzz in the cloud as well as a more lightweight version. That can be deployed even way faster because it's more lightweight, way faster. It's a bit more portable as well. It can be at the same time a bit less isolated because, as we said, the container will be sharing the kernel of the server, physical server. So by default, there might be some problems of a bit less isolation, but they can be resolved quite easily. So there are solutions for that as well. So given that I gave introduction of refresher for virtualization, I might as well just also give a refresher for 61850 for those of you who don't know it a lot. And it's important to give it because in the rest of the presentation, I will be using a lot of protocols based off of this standard. So it's nice to give a small introduction to it. So very quickly, IEC 61850, it's an international standard by IEC, and it is not only a communication protocol, which some people kind of confuse. It provides a whole systematic way of, at the same time, how can we, what are the data that we need to send, and how can we send this data? And to do this, it provides a data model so that defines these data, which can be a description of some instruments that we find in a substation. For example, a circuit breaker is called per 6150 XCBR. And this then, given this description, we then define how can we send this data through which protocol, and we also define how can we configure an IED. What is the engineering process that we have to define in order to here? Yeah, I give another. It's like a moving GIF that shows the segregation of the networks in a 6150 substation. So below, on the very bottom, you have the instruments. You have the circuit breakers, current transformers, voltage transformers, which are more physical processes. And you have the first communication bus, which is called the process bus, that will be getting digitalized in the current and voltage information from merging units. And they will be fed into the IEDs that will process this voltages and currents to detect some overcurrents or etc. And the highest communication level is the SCADA or HMI that usually is for transferring some less sensitive information or some control commands from the control center level as well. And here we see the main protocols that are mapped into the 6150 services, which are the ones that we will be using today as well for the rest of the setup. So we first have the sample value, which, as I said, sample value is responsible for getting digitized voltages and currents from the VTs and CTs. It digitalizes them and publishes them onto the process bus network. And it's a multicast protocol that's should be very quick with some strict real-time requirements. And the Goose is basically a protocol that's supposed to be it's also multicast and it's supposed to be sending tripping signals mainly between the IEDs within very small thresholds of 3 milliseconds to respect the transfer time of the standards. And these two protocols are important to keep in mind because then when the next rest of the presentation I will be referring to during the different type of security considerations and attacks that can happen. Speaking of security, it was during the start of my PhD, we considered the different aspects of virtualization. We started from understanding the subject, the aspect of how it would affect the engineering, how it would affect the configuration, how it could affect some simulation testing and economic assessment as well. And we thought it was based on the talking with all people, one of the main concerns about applying virtualization and substations was cybersecurity. So it was quite by default instinct to see how at least we can do a proof of concept study to assess, to do a first assessment of cybersecurity in virtualized substations. So this study, as I said, is a collaboration with TU Delft, mainly Nicola and other TU Delft colleagues that I did in June, July this year. So yeah, the motivation was for this is that we first want to understand how will the introduction of virtualization and substation increase the attack surfaces of existing digital substations, and will this also motivate, or is this motivated by the increase in the number of attacks on electrical networks? Is this also going to impact the number of attacks that can happen? The existing attack surfaces that are known and will be detailed a bit more tomorrow by Nicola are the SCADA systems, the IT, the physical IEDs as well from the control centers. And there are some new attack surfaces that can be impacted through the introduction of virtualization, including the substation networks that are now will be virtual and physical, and the IEDs per se that are now physical and virtual. And yeah, here we give very quick examples of the most famous attacks on grids that happened for the Ukraine, which actually impacted a huge number of customers, almost 250,000, with so many both in 2015 and 2016. So already this means that we should be cautious before applying anything, especially on very critical environments that can have a huge impact, huge losses. So that is why for the rest of this presentation, I will be more focusing on how mainly for first, defining what is the test bed that we developed in order to assess the cybersecurity, to do a cybersecurity assessment of virtualized IEDs. So I will introduce first the hybrid setup. I will also explain why we focus on virtual machines. So we will be doing virtualized IEDs and virtual machines and some cybersecurity around virtual machines. Defining the different attack surfaces, as well as giving you some vulnerability examples. So here I will do a quick presentation of the test bed at TU Delft. Basically, at TU Delft, they already have a lab. It's a control room lab where they have RTDS, which is a real-time digital simulator equivalent to Opal RT. And within this Opal RTDS, they also have some existing physical IEDs from a few vendors, such as Siemens, GE, etc., that are directly connected to RTDS network so that they can do some initial testings for some validation testings or certification for 6150 especially. And they also have connected to the same network a server, a Linux server running KVM hypervisor. And on this Linux server, we could have access to different virtual machines that can also have access at the same time to the RTDS network, which means basically that anything that is emitted out of RTDS, broadcasted or multicasted or sent, will be also reachable through this VM. So that is why what we call the hybrid test bed is basically a test bed that first includes a physical IED from a known vendor, and the physical IED runs a distance protection. In the virtual IED, we run inside the virtual machine. That is why we then focus on security for virtual machines as well. And inside the virtualized IED, we run a very, very basic overcurrent protection. And the idea in the first idea was, given this hybrid setup, to identify what are the new attack surfaces, or how can this hybrid setup be attacked if I am already inside this the RTDS local network. So as I said, first I will start by the first point of where we can do more attacks are the virtual machines. And for this, we did a small state-of-the-art review for cybersecurity of virtual machines. And what we found is that there are, yes, if I count correctly, 6 main attacks which can occur on virtual machines. The first includes or talks about virtual machine escape, which very briefly means that whichever data that is running or inside this virtual machine can be leaked. So we talked before about how they are isolated, but with the few vulnerabilities, you can actually leak whichever information is found inside a virtual machine to another virtual machine running on the same server. Or you can also leak from the virtual machine to the server itself, so to the physical server itself, which is basically you are able to reach a physical material just by passing through the software level, which is the virtual machine. This is quite a known or famous attack that can occur on virtual machines in data centers, with some examples by VMware hypervisors that include some vulnerabilities around this. The second is quite known, which is more on data stealing. So we can actually, if we have the image of the virtual machine, we can be able somehow to steal the image. And once you have the image, you can basically corrupt it as much as you want. The other one is at the level of the hypervisor. If you have some root access, basically, if you have access to the hypervisor, you can literally break everything that is running on this server. You can break all your VMs or corrupt it or anything else. Live migration, this occurs when you have more than one server. So imagine you have two servers, and live migration means that for some reason the first server gets broken, and you have to migrate whichever is running on the first server to the second server. And this is a service that is by default allowed by a few hypervisors, and it is one of the one of the very critical points, attack points that can occur, which means that it can be at the point where you are migrating from the first to the second, an attacker can come and corrupt the image. And for example, when you want to run it on the second, it's already corrupted in a corrupted image and wouldn't run really naturally. The last one, and the one that we focus on, is what we call availability or resource exhaustion. So imagine you are, to explain it simply, imagine you are running your PC and it basically gets stuck and you can't move anything and you have to shut down or whatever because all your CPU, RAMs, you look at Task Manager, they're all filled up. So this is an example of an attack that's quite often also can be known as a denial of service for virtual machines. So that can corrupt all your resources of the machine running, and we will see the impact that we observed because we focus on this type of attacks. So our objective for the tests was to identify if we do a resource exhaustion on a virtualized IED in a virtual machine, what impact it might happen on the running process. Here I also give a very summary of the surfaces. So we have the physical ID and the virtual ID. Virtual ID also includes the hypervisor. The hypervisor is the software, which is you can consider it like the OS of the server. They can have a few vulnerabilities, like from the known VMware vulnerabilities. This also, which is quite detailed, but if you know the power consumption of your server, you can also do some quite very difficult, complex attacks on this hypervisor just by understanding what is its consumption, electricity consumption. Some remote debugging tools at the level of the virtual machine or the container. There's a lot of attacks that can occur at the level of shared cache, because it's a low-level detail, but even though they are isolated per se, there is a small cache level that is not always by Intel system. It depends on the CPU that is still shared. And sometimes these can be manipulated so that they can reach to the VM escape attack that I just previously mentioned, which is also quite a sensitive way to break your VM. There have the CPU, or you can have some another one that it's important to mention now before explaining the tests are scheduler reprioritization. Explained simply, when we have a real-time system, we have what we call real-time scheduler. A scheduler is it works at the level of the kernel in the operating system. It's responsible to ensure that your process is always being given a space of CPU so that it can actually perform the calculations. And it has to run in very real-time deterministic way with high priority for real-time systems. And one of the type of attacks that you can do is you can try to break this scheduler mechanism, which means that this process, instead of being given access to CPU every X second, if you try to give it access with high priority, you try to break its priority and give it every X plus 10 seconds, then you will lose real-time performance, and it can lead to quite detrimental impacts for real-time systems that we are talking at the level of milliseconds. Yeah, here another known example is when you have some open ports. Open ports are, you can understand them as something that is allows you as an external to have access to the IED HMI, for example, to modify something at the level of the configuration of the IED. And sometimes if you have some open ports, they can be vulnerable, and through an open port, you can then have access to more low-level details that will then, for example, change the code that is running inside an ID that could be now running something totally different or totally malicious. So these are the examples very quickly for people that are more into cybersecurity, like Nicola. What they usually, how now I mentioned in the previous slide the different types of surfaces or vulnerabilities that can happen, but to really know what are these vulnerabilities, that is an international database that's called the NIST, National Vulnerability Database, that can tell you what is vulnerability that can happen or exists in a certain equipment. So here there's an example of the open port vulnerability that can lead to breaking a denial of service of the system. Here there's an example for the VMware hypervisor, which leads to the virtual machine escape. So basically, this quickly explained, this if someone malicious with no authentication even needed had access to a virtual machine that is also configured with a storage controller. If they send a specific packet, they will be able to reach other VMs that they are not supposed to even reach, or they would even reach and break the host system as well. And this is another quick example of a denial of service from Siemens relays. This is also was quite recent. This is another example of a problem that can occur with real IEDs. Here there is an open port, and simply explained, there was a problem in the code somewhere with a null reference, which means that by sending an HTTP request with a specific packet, you could actually break the IED, and it leads to a denial of service of that IED running if you were able to send that malicious packet. So these are some examples very quickly of the vulnerabilities that can actually exist. So these are real examples of vulnerabilities that someone malicious can look into them or find them without knowing, and use them for bad reasons as well. So here I will just give some time for any questions before continuing. If someone from the audience or online has any questions for this before continuing the description of the setup, tests, and attacks that we did. Yeah, if anyone online, you can just open your mic as well. Yeah, Conrad.
Two quick questions. So first question is, you very well pointed out cyber threats, virtualized IEDs. Are there also some benefits we gain in terms of cybersecurity? Virtualized IEDs? it's the first question. And second question, you pointed out very well the benefits of virtualization, but are there also some negative sides? For example, I could imagine that the code is less efficient than the hardware. Maybe you could rate on these things.
Okay. For the first question on the wait. It was on the are there advantages for cybersecurity? Yeah, I can respond by and the literature, or as they now say, they would say that given that it's a more flexible or easily upgradable system, you can also easily patch it. So for example, if they found out there's a problem, it could be very easily patched with a new image or a new upgrade, and the whole process of virtualization also will support this new patching quite rapidly. So that's quite an example of what can be an advantage compared to physical system like the relay from physical IED could be a bit more difficult, especially when you have many at the same time. For the second question on the disadvantages of virtualization in substations, one of the main disadvantages could be that it's a new technology already, so it's not very well educated. For power system, people are not very known to have such type of information advanced, so they might be hesitant. Sorry. What's that? Okay, sorry. So yeah, since it's a new technology, so it might not be very known or well educated, so there might be hesitations. There might be some issues about maturity as well. It's still novel technology that's not totally mature. There might be some interoperability. As I mentioned, for now, there is no one single way of doing stuff. Everyone is still just doing proof of concept, demonstrations. If someone's doing with the VMware, someone else is doing it with containers. So yeah, for now, it's still very wide and yeah, I think these are one of the main challenges of acceptability, interoperability, and maturity in terms of even demonstrations of everything. Any other question?
Did you test some platform? You mentioned Proxmox previously on the slide. Did you test some platform of virtualization?
Yes, I will. Right after this, I will start explaining the tests. Right after now, I will. In the next section, I will start explaining the different tests that we did.
Okay.
Okay.
Moment. There is another question.
Yeah, I have a question about cybersecurity. What are the biggest threats of cybersecurity? We need. Also, what are the challenges? Hardware. They could have different, let's say, operating system or environment. So in that case, are there any, let's say, standardization work need to be done for that? And what standards do this?
For the first one is the major cybersecurity concern. From what we just saw or analyzed, there are different. There is not one per se that is major, but it's just that the introduction of new attack surfaces, whether it is at the level of the virtual machine or at the level of the hypervisor, this is the introduction of a new ways that you can now attack could be one of the main concerns maybe. How we can protect it. I'm not a cybersecurity expert, but maybe there are different mechanisms that Nicola will talk about maybe tomorrow a little bit as well, that there are ways to protect it. It's just that now what we are explaining is we are demonstrating that we have to pay attention, and this is what can happen in case it is not protected. So it is more of an awareness now to incite people to protect even more. And for the standards, for now, there's some groups starting to work on virtualization, like with Thierry in IEC, with some participation of IEDs as well, another DSO. And we have some other groups in CIGRE and even IEEE that are starting to working on this subject in terms of defining different reference architectures and etc.
Just want to follow up on cybersecurity. I have let's say if you have virtualized different devices and if one device the environment compromised, then that could affect all the rest. Okay.
If I listen this, if one device is infected, would it affect the rest? I would say not necessarily. It depends what are you exactly attacking. If it's already attacking just a single VM, but it's not a virtual machine escape, so it might not impact the other virtual machines, or are you attacking the hypervisor on a single server, so it might not affect the other server. It depends really on the attack that you're doing, or or if the network is already quite segregated with VLANs, etc., and you had access to just one, so it might be invisible for you the rest. So it really depends on what is the attack that's being implemented. So it might not always be the case.
Whether a compromised device inside substation is the device or not on which device level directly reach screen. If there are device ID or either in the levels passes to the passer directly and exactly what we're going to discuss tomorrow. And security wise, proper network segmentation and but if you wanted to avoid device to act monitor what's happening device network. But tomorrow.
Please. The mic.
I actually wanted to contribute to the discussion that Gwange started. I think it has something to do with what you mentioned about resource exhaustion, because how I would expect an intruder to actually effect the resource exhaustion, creating something we call zombies. I think you know about zombies with DDoS. And what you do with zombies is one VID is infected, or you infect this, and then you use those VIDs to launch in other areas of your substation. So indeed, for sure, you could have that case where one VID other VIDs. So that also has you said about resource exhaustion, because that's what ends up happening. In that case where the zombies are doing something else as opposed to sending ghost messages. So I believe there's a bit.
Okay.
We have another question.
Okay.
Also, so you can go ahead.
Okay, so I will continue with the rest of presentation, because I know that online there are people that that are only available at until 4. So that's why I was suggesting to continue. So now I'm gonna talk about the case study that we did for the tests on the test bed. What we did here was using a case study on protection selectivity, because as I explained, we had 2 IEDs, one virtual running over current protection and one physical running distance protection. So we kind of resorted to a concept called protection selectivity, which basically means that you want to protect a certain zone on the grid by isolating the minimum possible and disrupting, the minimum possible zone on the grid. Using this protection concept coordination. So that is why for us we took we have two protections, but we have the virtual IED, which we can say that it is more the curve to the left, so it acts more on a smaller zone faster. Then the physical IED that will act on a bit larger zone with some higher threshold. And another motivation of doing this protection selectivity case study is that usually, maybe you have protection experts that know more. It's like it's quite difficult to ensure this complete selectivity because it's quite expensive as well in terms of development or infrastructure. So as a motivation, we said that by using some virtualized infrastructure, we might try to cut down some costs by using the more centralized IEDs on a central server. You can have many different virtual IEDs running that can be having the concept of doing selectivity or protection selectivity or etc. in parallel with the physical IED. Instead of having 2 physical ones, we might try to cut down in terms of architectures or costs. So, so that is why in the next of or for the rest of the demonstrations, what we did was first we tried to simulate different cyber attacks that can happen either at the level of the physical IED or at the level of the virtual IED. And the concept was to demonstrate that if you attack the physical IED, the virtual IED will still be running and will clear a fault in case a fault happens. And the same, but the inverse. In case we attack the virtual IED, then the physical IED will be the one that will be taking the relay and ensuring that the system rests in process. So this was a little bit the idea for the rest of the tests that we did on the test bed. every time we attack the virtual ID, we try to expect or that the physical one or the inverse will be the one that is taking the relay, and then with the final objective of ensuring that our system will still be working operation as securely and safely as possible for the electrical grid. So yeah, here is a quick summary for what I just said. It's a very interesting area of research, but at the same time, electrical grids per se are also target for many cyber attacks. So with virtualization, you are somehow introducing more surfaces or ways to attack and lead the attacks to grid. So that is why it is very important to consider some security by design to, in advance, prevent anything, any problems from occurring, which motivate the rest of the tests that we did on this test bed. So here I give again the examples of the tests that performed. There are 3 major tests that were performed on the test bed, or they are also attacks that are quite known. The first is a port scanning attack that I will explain, the resource exhaustion on the virtualized virtual machines, and the third is goose or sample value injection. I will explain in detail all these different attacks with some examples of the results and some demos as well. So here is some rappel. So it's like again, I show you the photo. Always, you should keep in mind that we are either trying to attack one or the other and not both at the same time for the sake of this tests. So the first one, each time we also did a set of normal conditions. So in case of normal conditions, we just run an IEEE 5-bus system with some voltages and current measurements that are normally running. And this is defines our baseline, a normal case where nothing happens. Another per se case what is also normal between quotation is when we have a fault occurring on one of the on one of the buses, and you would expect that to clear the fault, the circuit breaker would open normally if there is no attack. And then we did the port scanning as well with different level of aggressiveness per se. The resource exhaustion that was run at the same time in normal case where nothing happens, no fault happens, and in the case where a fault happens. And this is quite important to test in case a fault happens, because these attacks can actually not run just for a couple of seconds. They can be running for a long time without knowing. And during this long time, for some reason, there can be a real fault that occurs on the grid. And that is why we would like to know, in case this virtual machine is already attacked and a fault happens, what impact can this attack have? As well as with the goose and sample value injections. So the first attack is the port scanning. A port scanning, simply explained, is what allows you to identify the topology of your network, basically, if you have access to a network, you can discover what are all the devices connected to that network. You can identify, then you have, for example, in our case, we detected when we ran and what we call an Nmap scan. You detect that you have the RTDS, you have one physical IED from Siemens. You can also detect that you have another IED from etc. And this can be done by an attacker in case he was able to reach by some way, for example, through a malicious phishing email to the substation engineer or access to the engineering workstation. He could, for some reason, be able to discover this network. And once you discover what you have, it's like you have a map. And once you have a map, you can try to also discover, are there any destinations that can have some open port vulnerabilities that I mentioned just before. So this is usually this is what they might be used in different levels of aggressiveness. Between quotations means that they can discover the topology without you knowing. There are definitely systems that exist to prevent such occasion from happening by detecting any intruder. But yeah, by using an map, we first define the different points that might have any open vulnerabilities. And this is quite a passive attack that doesn't have a direct impact, but might be strategical, because it's then you can study different next level, more advanced attacks that can happen later on. Now, this is the description of the resource exhaustion. How did we do it or simulate it? Here again, to emphasize that we are not playing the role of the attacker. We are just assuming that an attacker was able to reach by some way this local network, and he was able to do a resource exhaustion attack on the virtual machine running the virtualized IED. And what we do here, we simulate the impact, because by simulating the impact, we can also understand what are the effects that can happen on this attack. So how do we actually simulate the impact? We basically run different stress on the VM. By stressing the VM, you are kind of like consuming all its CPU, so that the virtual IED process will no longer have access to the CPU and will eventually lead to resource exhaustion or denial of service for the virtual machine. You have different level of stress that you can put more on your system, so that it might almost never have access to CPU. And this here I talked about, mentioned, is the scheduling priority. So here also, to simulate a scheduling reprioritization attack, we also changed the priority of the process, running the virtual IED. You can do it by Linux system, easily change the priority. This is to simulate the case where a real-time attack on this real-time Linux system happens. So as I mentioned, the purpose here to just simulate what can happen as an influence and what influence it has on the real system in case a fault occurs as well. Now, another type of attack is what we call goose or sample value injection. Here I can explain it with a metaphor from a paper that I said. It's like when you are watching a Hollywood movie with guys robbing a bank, and they crack into the security cameras, and instead of the cameras really recording or saying what is actually happening with them running inside, they replay I don't know, another static image without showing them actually going in. So with the same analogy, we can say that the purpose of a goose or sample value injection is to kind of inject a packet to simulate a fault happening on the grid when actually nothing is happening. So you would force somehow the opening of a circuit breaker at the wrong times, or you can fabricate abnormal conditions as sample value voltages and current measurements. You can replay them, and also the IED would then think that there is a problem, or when actually nothing is happening. It's just a malicious actor that wants to compromise something on the grid. And for this, you can develop a few simple code that you can use. It was with the help of other colleagues at TU Delft that already did some, but we reutilized it, where you can spoof. Spoofing means that you can read a packet, a goose real packet, and then the attacker would use this real packet change from open circuit breaker false to open circuit breaker true, and then inject it or replay it back to simulate a goose injection. So this is what we mean by a goose injection or sample value injection attack. Yeah, here you can see from false, you can change it to be more true and inject it at different sampling times from the traditional, more sequential sampling rates of goose protocol, for example. Now, here in terms of major results or observations, I would like to more assume. So there were three major patterns that we observed while running the resource exhaustion attack on the virtual machine. And in parallel, there is a fault that happens. You will see in the figures next figures. But imagine the resource exhaustion is running and a real fault occurs. Then what can actually impact does it have on the trip signals? So for this, we observed three major patterns that might happen. The first is, maybe you already would guess it, is that there are delays in sending the tripping signal. So the delays can be from a few milliseconds to over 200 milliseconds, which is quite impactful, actually. And the second is what we call a latch of the signal. This was a quite weird behavior, but very simply explained, it means that you would suppose that once the trip signal from goose is sent to clear the fault, usually there's a reclosure mechanism that says after a few seconds or something like that, the trip signal should pass back to false, so that the fault is cleared. It won't, or the circuit breaker won't stay open forever if it's not a permanent fault. So another behavior that we observed while running the resource exhaustion attack is a latching of the trip at true. So which means that the value of the trip stayed true for sometimes over 200 milliseconds, saying that you should keep it open because of this delay in treating the signal due to having barely any access to the resources during this attack. And the last one is the most extreme case, is actually the virtual IED never even detects the fault and doesn't even send a trip, which is one of the extreme cases. And from 27 simulations, 62% of the cases just had some delays. 48% had delays with latches. So it's both. That's why it's more than 100 total. And 7%, so twice only, there was a total drop of the signal. It never detects the fault at all. So here you can see a more schematic description of how attack happens. So first we start by running normal values. The circuit breaker continues to be closed. At some point there's a fault that occurs, and keep in mind that the resource exhaustion attack is still running on the virtual IED. While the resource exhaustion attack is running, so it's already started, you can see started, and after it started, the fault occurs. Here you see that only the IED signal will. No, here it's the inverse. Yeah, here it's the resource exhaustion. So here it's only the physical IED that will trip and clear the fault. And clear the fault here. We don't see the reclosure, but the fault will be cleared and the current passes to 0. Whereas the physical IED never trips in this example. So it's the third pattern where the physical IED never trips. So here it's just to demonstrate that when an attack that blocks the virtual IED occurs, the system will still trip, but only due to the selectivity from the physical IED. Now here you see the inverse. Here there was attack that was attacking the physical IED. So here you see that in parallel, we were running another sample value injection attack on the physical ID. So in green, which is the virtual ID, it was only the virtual IED that tripped following a fault. And the physical ID never trips because the attack was actually targeting and blocking the physical ID. So here, with these two graphs, we kind of demonstrated our behavior that we wanted, which is we never want the system, power system, to break down totally. In case the physical was down, the virtual operated, and here, in case the virtual was down, the physical operated, the inverse. So this was the first selectivity proof or demonstration of the test that we did. Here is a more in-depth explanation of the results with the delays. So to the left, we see the delays, which is the difference, the delay between tripping from the virtual ID minus the tripping from the physical ID. And you see that the delays, when it's negative, it means that it's normal behavior during the resource exhaustion attack. And when it's positive, it means that there was a significant delay in sending the virtual ID tripping signal, and which could almost, at one point, it was almost 250 millisecond delay in sending the virtual ID trip. And at the power system side, here you can see the impact of the delay in sending the tripping signal. So instead of clearing the fault and the currents going back to zero in just under 10 milliseconds or something, with the delay, it increases the time. You can see that the sinusoidal signal is a bit shifted to the right by a few milliseconds, which people that are more experts in transients can understand the impact of a few millisecond shift in tripping or opening to clearing the fault as well. Here you see the impact on the CPU resource exhaustion. So as I said, this to the top in blue is the virtual machine that is being stressed, that is being exhausted. So its CPU, it's topped at 100%. So basically means that you are almost breaking your VM. And to the bottom is the process, so the CPU access of the virtual ID process. So this process algorithm running on this VM that is being at 100% CPU access with stress, what is its access to CPU usage? So in black, you see on the bottom, at normal cases, it was almost quite consistent at 15% CPU usage of the process. But when there was being stressed, it was sometimes being at 0% for quite some time, or less than 10% for quite some time as well. And here you see it more clearly because we said when the signal is dropped, you can clearly understand why the signal was dropped, because if you see the CPU usage of the process, it was almost at 0% half of the time, which means that the process was barely having any time to process all the packets that are being sent. That is why it was never actually able to detect the fault or send the trip, and that is why we also categorized it as vtrip dropped. Sorry. Here is the example of how we did the goose injection. It's also the same thing. Here you see where the fault starts, where the goose is injected, how the system perturbates. Here by injected, I remind you that it is the example where we replay a sort of scenario where the system is supposed to be running normally, but this malicious actor wanted to do some movie stunts and send a packet that says there's a fault. So you have to open the circuit breaker and see how it impacts the system. So here we also had some strange behaviors from the physical ID. which you can see here on the graph. So here, when we injected a false stripping for the physical ID, for some reason that we can't necessarily 100% understand, given that the physical ID is for us a black box, but the implementation of it added a delay of almost 1 minute to reclose, to do the reclosure mechanism, which means that here you see that circuit breaker, it took almost over 1 minute to reclose it back, instead of just a few seconds. That was a very behavior that we had because of doing the goose injection attack for the physical ID. Here also I might mention that during one of the simulations, we had some time synchronization problems inside the virtual machine, inside the virtualized ID, which basically means that the virtual ID time was delayed by 3 seconds compared to real time, which is the clock, real time synchronized to a master grand clock in RTDS. And apparently this is quite known issues for virtual machines, that some system administrators are known, and especially for some production environments with virtual machines, which was something that we did not know necessarily in advance, and thought that it was worth mentioning as well to consider while doing the performance or considerations, because it can also might be another point of attack if someone breaks the synchronization of the VM or something else, drifting the time, and by default it will have some important impacts as well on the grid opening and closing. And for now, for here, I will very quickly show you in a few minutes, for those who rest online as well, how we were doing the attacks. So here we had, if it plays. Huh. Yeah, here I will just quickly show you the environment where we were able to do the attack. So to the left, you see the RTDS 5-bus model configured with the sample value and goose cards, networking cards, and the IEC 6150 goose as well, to trip the signal, to receive the tripping signal and subscribe to the physical ID and virtual ID goose trip inside RTDS model as a subscriber. And in the model, we could also simulate all the currents, voltages, and simulate the faults. And here to the right, you start seeing the virtual machine environment. So we had 2 virtual machines. The first runs the VIED process that I told you about. And this VIED process is the VM that will be that we will directly use to do other type of attacks, and another VM that we will use exclusively just to do the scanning and goose and sample value injection attacks. Here I start by just simulating a fault. So when it's red, it means the circuit breaker is closed. When it's open, it means that there is a fault that occurred. To the right, we can see that the VIED logs that explain that the fault has well been created and the stripping signal goose has been sent. And then I'll start showing, here you see the different data points from RTDS, the tripping. And here I show you first, I guess, how we did the goose injection. So from another VM, we replay a stored packet that we had already collected with value trip equal true, either a goose from the VID or physical ID. And we inject it while the RTDS simulation is running. And you can see here that once it's injected, it should turn green. Yeah, here you see it's green, which means that we, in normal conditions, we opened forced the opening of the circuit breaker. From both a goose configured for data set from the virtual ID and a goose from the physical ID. It depends which access, where you access the goose. And to the right, you can see the goose message with value true. I think here, yeah, here we send the packets of goose, and here you see the packets with the value true of the goose that we just injected. Let me see if it's saying. Yeah, but basically on Wireshark we can verify that this goose has been well injected onto the network. And here maybe very quickly as well show you the resource exhaustion, how we were doing it. So here you see on the virtual machine running the VIED process, how the CPU consumption of the virtual machine and what is the consumption CPU of the process that is running the protection over current. So here here you can follow the CPU. First, we change the priority by the pseudo renice of the priority of the process. And when you change the priority, so by default, it will have less priority to access the CPU as well. And here we start stressing, pseudo nice, we start stressing. You can see here, I don't know if you're now seeing the peak of you checking the CPU, you see it's peaking at 100%. So this demonstrates the start of the resource exhaustion attack. And in parallel, we are running RTDS, and in parallel, we can send a fault, simulate a fault. And then I collect the data, the trip signals, to see if there was a delay or a drop or whatever, a latch. And the last one is showing you the impact on library 6150. For those that are a bit more known, here you see that while running the resource exhaustion, the sample value count or goose count, because it's usually sequential, 1, 2, 3, 4, 5, till I don't know how much, 4,000 maybe. It's usually sequential, but when we do the resource exhaustion attack, it starts giving you some warning that we expected value of packet number 2000 something, but we received 2200. So there's a delay by a few hundred packets that are being dropped or being not even considered by the process due to the resource exhaustion attack happening in parallel. That is all I had for today. Yeah, as you know, it's I reiterate the purpose here is that it's more of an awareness study on what might go wrong. What are the new types of attack surfaces that can happen with virtualized IEDs in substations? What are the effects? The main effects are they can have impacts on physical entities, not only logical, because physical entities, you can open circuit breakers, you can destroy some physical equipment with like a critical impact. So that's why it's quite important to do precautious preventive measures, some security actions. And we know that in the study, we didn't necessarily study the preventive measures, as I am not necessarily a security expert. But with Nicola, maybe tomorrow, he will give you some examples of how we can protect the substation network or architecture from these type of attacks in advance. And that is all. If someone has any questions now, we can take from both online and physical.